Good morning, ladies and gentlemen. My name is John Moroney. I'm the Business Support Manager for Hach in the UK. And I just wanted to start this morning by welcoming you to the fourth in a series of webinars from Hach on wastewater applications. The presentation will last approximately 25 minutes. And as always with our webinars, we'll keep the questions until the end of the presentation when we'll answer them then, or if need be, we'll take them offline and discuss them with you further. The way to ask a question, if you haven't been on one of these webinars before, is to type your question into the panel on your screen on the bottom left-hand side. And then I'll be reading those out and getting those answered, as I say, at the end. The fourth presentation in our series this morning will be given by Martin Butterfield. It's entitled Phosphorus Compliance, Advanced Chemical Dosing Using Real-Time Control. Martin Butterfield is one of our application development managers, and he's a real-time control optimization specialist for Hach. Martin's worked in the water industry for the last 30 years and has been with Hach for the last 20 of those, so he's got a wealth of experience to bring to this subject and to the subject of real-time control. So I'll hand over to Martin, and I'll be speaking to everyone then again at the end when we have the questions. Over to you, Martin.
Thank you for your introduction, John. Although I will be talking about the removal of phosphorus from municipal wastewater streams, the process and challenges of phosphate removal are very similar to those experienced in the industrial wastewater applications. Before I delve into the process of removing phosphorus from wastewater streams, I would like to spend a little time in describing what we are trying to measure and remove. Before attempting to achieve a target value of phosphorus, we need to understand what the parameters to be measured are and how this value is to be measured. Phosphorus in wastewater is analysed to produce three distinct parameters. So firstly, we'll deal with soluble phosphorus. This is mainly, but not exclusively, orthophosphate, and the analysis is carried out by filtering the sample to at least 0.45 microns before analysis. The results can be quoted as milligrams per litre PO4 or milligrams per litre PO4 as P. Then total phosphorus. To achieve a value for total phosphorus, the sample has to be treated in two distinct ways. Firstly, the sample bottle is homogenized and an unfiltered sample is analyzed, with only gross solids being excluded from the analyzed sample. Secondly, the sample is then treated with acid for 1 hour at 100 degrees centigrade to dissolve or hydrolyze the solid particles before cooling, and then measuring using the same method as that used as the soluble phosphorus. Now, there's a third parameter now which has come to the fore, and that's total reactive phosphorus. This is an orthophosphorus analysis carried out on a settled but not filtered sample. So the sample analysed will contain some suspended particles that are slow to settle. Some of these particles will be hydrolyzed into orthophosphate by the acidic solution used in the phosphate test, but there is no digestion step to complete. There are two schools of thought regarding this test. One is that it replicates the availability of phosphorus compounds to biological processes much better than the total phosphorus test does. The other says it's easier and quicker for the laboratory to perform the test as there is no filtration or digestion step. Now I'll go on to discuss the forms of phosphorus in wastewater. These break down into two main groups, soluble, and these subdivide into three subgroups. These are soluble reactive phosphorus, which is orthophosphorus with a formula of PO4. Acidic hydrolyzable phosphorus. These are short-chain polyphosphates which will hydrolyze at room temperature into orthophosphate when in contact with the acid used in the phosphate test. And lastly, soluble organic compounds. The exact nature of these compounds will depend upon their source and whether they will react to the phosphate test. Their exact composition is not important, but some of these may be hydrolyzed by the chemistry of the orthophosphate test. Now we go on to particulates. Depending on the particle size, some of the colloidal phosphorus compounds may be transferred into the soluble fraction by passing through the pores of a 0.45 micron filter. The inorganic fraction of the solids would not be measured in the total p-value, as generally inorganic salts of phosphorus are insoluble apart from sodium, potassium and ammonium, but we'll come on to that a bit later. So where does all this phosphorus come from? In a municipal wastewater treatment plant, it's estimated that just over 2/3 of the phosphorus comes from the food that we humans eat. The next largest is dishwashing and laundry, which accounts for around 16% of the load. The phosphorus added to drinking water to pacify lead pipes accounts for only 6% of the phosphorus load, and that's being dosed at between 1 and 2 milligrams per litre as orthophosphoric acid. And surprisingly, industrial discharges generally account for less than 1%. So why are we measuring phosphorus? Well, phosphorus is one of the supporting physico-chemical elements named in the Water Framework Directive. The list includes pH, ammoniacal nitrogen, dissolved oxygen and alkalinity, and these are required to be monitored under the Water Framework Directive. The problem comes when too much phosphorus is present along with other nutrients, including nitrogen. In enriched conditions in rivers and lakes, the natural distribution of plant species is imbalanced, favouring fast-growing species which are more readily able to take advantage of the available nutrients. This causes over-competition and a reduction in the slower-growing plant species, with a knock-on to the organisms feeding on these slower-growing species and hence upwards up the food chain. Another drawback is during nighttime hours there is an oxygen sag in the river or lake due to the overgrowth of plant matter respiring carbon dioxide, but no oxygen being produced to counter this. Other drawbacks are the clogging of normal river flows, slowing the velocity and hence risking summertime flooding in storms, and the production of algal blooms which can block intake filters of drinking water plants, and some conditions promote blue-green algal blooms which can produce toxic compounds, making the water unsuitable for use for drinking water or killing other organisms. When these blooms form, the thick mats of algae on the surface can prevent sunlight from reaching lower down the water column. The next section covers how phosphorus can be removed from wastewater streams. Firstly, all biological treatment processes remove phosphate from wastewater to some degree, simply by the action of cell growth, as phosphorus is one of the key elements required for life. Normally cells comprise between 1 and 2% of their mass as phosphorus. However, in bio-P removal plants, a different type of bacterium is selectively enhanced, and these are known as PAOs, standing for polyphosphate accumulating organisms, and these can contain between 5 and 7% phosphorus. To encourage the growth of these bacteria, they require two conditions. An area of the plant rich in volatile fatty acids, and this area also has to be free of oxygen, nitrate and nitrite. Under these specific conditions, in the anaerobic zone or the selector zone, these PAOs expend energy to take in the VFAs by converting their stores of polyphosphates into orthophosphate, which is then excreted through the cell wall. The VFAs are stored within the cell as polyhydroxybutyrate. When the cells are transferred into the aerobic environment, the orthophosphate is reabsorbed into the cell and the polyhydroxybutyrate used to form new cells. This uptake of phosphorus greatly exceeding the excreted amount, resulting in a net reduction of orthophosphate in wastewater. Biological phosphorus removal has some disadvantages. The phosphorus incorporated in the cells can be released if the cells are under stress. Digester liquors that can contain very high concentration of phosphorus and may have to be treated in a side stream in order not to overload the inlet of the plant. BioP removal rates are temperature dependent, therefore faster in summer and slower in winter. And it would be recommended that a backup of metal dose is added to the plant just in case there are problems with the biological system. Next we go on to the chemistry of phosphorus removal. When ferric salts are added to wastewater, two reactions occur. A direct reaction between the ferric ion and the phosphate ion. Now, phosphate salts are sparingly soluble in water, depending upon the metal used. The water temperature and pH depending upon the metal used, the water temperature and pH. For example, in aqueous solutions between pHs 7 and 8, ferric phosphate solubility is between 0.2 and 0.15 milligrams per litre respectively, and we'll come back to this figure later. If we were just dealing with a solution containing only soluble orthophosphate, that would be the end of the story. But the consent is for total phosphorus, so the particulate loading has to be dealt with. When ammonium or iron acidic salts are added to water, the metal ion reacts with the water to form a fine flock of hydrated metal hydroxide. In the process of forming these flocks, the surface charge of colloidal particles is disrupted, and the colloidal particles begin to agglomerate. As the flocks form, these particles are attracted to and dragged out of suspension as the heavy flock sinks through the water column. The two main metals used in phosphorus removal are aluminium and iron. For both precipitation of phosphorus in the primary settling tank and also dosing after the ASP for precipitation in the final settling tanks of an activated sludge plant. Until recently, the dose of the metal salt has been based on the results of jar tests alone. However, there are limitations on jar tests, mainly because the test timescale is only 1 hour, but at dry weather flow rates, the retention time in a settling tank could be between 6 and 8 hours, or at full flow to treatment, the retention time could be down to around 2 hours. As can be seen from the graph, increasing the molar ratio of metal to phosphorus increases the percentage removal, with aluminium being more effective than iron for this removal. The jar test would suggest a much higher molar ratio of metal to phosphorus is required, but in practice, this is not the case. There are two profile dosing regimes used to adjust the dose of metal at the inlet of a wastewater treatment plant, these being flow paste and time paste. In flow pasting, the dose of precipitation metal is proportional to the flow entering the works, and obviously at time paste, where the time of day and, depending upon the nature of the catchment, the day of the week determine the dose rate of the precipitant. The left-hand graph shows the phosphorus concentration at a particular works against flow, and this can be seen that there is no credible relationship between the flow of influent and the phosphorus concentration. The right-hand graph shows the same water treatment works and the same data, but this time the phosphorus concentration is plotted against the time of day. There is now a distinct trend. However, the peak load, which occurs somewhere around 11, can still vary between 40 and 100 kilograms per day. The minima being around 7 AM, and that varies between almost 0 and 40 kilograms per day of phosphorus. The use of storm suppression dose rates to prevent overdosing during storm events is also not sufficient to cover all eventualities. This slide shows the works with a catchment of around 30,000 population equivalents, and the normal peak profile at average flow rates entering the plant versus time. This is the blue line. The red line is the phosphorus concentration at 1.5 times the average flow, which is really a storm flow, and this is plotted against time. In this real example, which has a consent of 1 milligram per litre phosphorus, a storm event will trigger the dosing system to stop the addition of metal. Please note that both lines follow the same diurnal pattern, but at the maxima there is 50% difference. This slide shows the same data set, but this time the load has been to be removed is graphed rather than concentration. During a storm event, the load to be removed is reduced due to the dilution. However, at peak load periods, the load to be removed is only reduced by around 10% compared to the average flow loads. If a real-time control system is used to monitor the load entering the plant, then savings can be achieved. Here we have a site using flow pace control for a precipitant dose control. The region between the arrows shows a rain event. The yellow line is the precipitant dose and the green line the phosphorus load. As the increased flow caused by the rain event enters the works, the flow pace system increases the precipitant dose according to its pre-programmed profile. After a period, the system switches to storm suppression dose of 10 litres per hour, which is still too high when you consider the load to be treated. This graph also shows that it's difficult to judge when to return to the normal dosing profile, as in this case, the system has returned to profile dose too early and hence dosed an excessive amount of precipitant, as the phosphorus load is still at its minimum. Here we have the data from a site with a mainly municipal catchment and a population equivalent of around 500,000, showing 2 rain events occurring a few days apart. In storm event number 1, the flow peak enters the works marginally ahead of the phosphorus peak concentration. This is caused by the higher flow scouring the settled solids in the sewer network. Please note that the phosphorus concentration is only elevated by around 10% above the normal peak value for that time of day. However, the phosphorus load entering the plant has increased significantly due to the increase in flow. Load being flow multiplied by concentration. In this case, profile dosing with storm dose suppression would have underdosed the phosphorus load being carried into the plant. In storm event 2, which occurred a few days later, the sewers are still relatively clean, and as the flow peak enters the plant, the phosphorus concentration reduces rather than increases, as happened in event number 1. Flow returns to normal ranges after about 5 hours, but the phosphorus concentration does not return to normal levels until around 11 hours after the peak flow entered the works. In this situation, a storm suppression dose would have been turned off after the flow returned to the normal range, leading to an overdose of precipitant. The next section shows how real-time control system can achieve compliance and savings in precipitant. By measuring both the flow of sewage entering the plant along with the real-time value of orthophosphate, an RTC system calculates the required dose based upon a number of factors. These being the target concentration required for compliance at the outlet of the works, the biological uptake of phosphorus by the plant, which enables the RTC to calculate the load to be removed, and hence the molar ratio of metal to phosphorus required to achieve the target value at the outlet. This gives a value of the precipitant dose to be applied. It also assumes a feed-forward system is employed, dosing precipitant into the screen sewage with the flock forming in the primary settling tanks. PRTC can also operate as a feedback controller, measuring in the final effluent and controlling the precipitant dose before the mixed liquor enters the final settling tanks. Real-time control of precipitant dose provides the correct dose at the correct time. Site conditions are taken into account. Dosing can be reduced or even stopped during storm events. Real-time control provides compliance with both phosphorus consent and metal consent, and it also prevents overdosing, which could cause alkalinity issues. Here we have a schematic for both an open and closed loop, an open loop or feed-forward controller, and the closed loop or feedback controller. This next section covers the equipment required to make the measurements in challenging conditions found at the inlet of a wastewater treatment works. Until recently, it has not been practically possible to measure orthophosphorus at the inlet of a municipal treatment works due to the challenges presented by the sample, with fats and greasing blocking filters. Hach now have a sample preparation system which overcomes this, using a sintered filter which is cleaned by air scour and a hypochlorite backwash. When this sample system is combined with our online phosphate monitor, the Phosphax SC, and our real-time control system, it is possible to provide load-based precipitant dosing control at both the inlet of the works in an open loop or feed-forward configuration, and at the end of the biological phase in a closed loop or feedback configuration. This slide shows the components of the filter and the filter probe in use. The size of the filter itself lends it to use in final effluent where water level is low during low flow conditions. In this case, the filter can lay flat in an outfall channel. Although it's possible for the end user to program a PLC to carry out the functions of the Hach PRTC, the PRTC module already contains the control algorithm, the interface between the analyzer and the PLC. It takes into account the varying molar ratio required for precipitant dose with concentration, and the biological phosphorus uptake. Hach RTC also provides the interface with the dosing pumps by either analog or digital communications, as well as an interrogatable user interface and data logging. All of these are possible to program into a PLC or SCADA, but at what cost? And how long would it take? In the Hach PRTC system, it's all already there. Here we have a typical installation of a PRTC system, and it's showing its interfaces with the rest of the works. In the next section, we will look at two case studies using PRTC. This first case study looks at a plant in the northeast of the UK which suffered from high industrial loads, peaking at up to 60 milligrams per litre orthophosphorus. The system installed was open loop control, dosing ferric sulfate into the screen sewage to settle the flock in the primary tanks. Before installation of the PRTC, the standard dose was set at 30 litres per hour. As a result of installing the PRTC, feed-forward load base control, the phosphoric dose was reduced by 45%, and the site was compliant in both phosphorus and metal. Please note, the target for the PRTC endpoint was adjusted over a period of time, which is the green line on the graph. And this was as the site operators became to accept that the PRTC would actually control the dose. Hence, the target phosphorus concentration started at 1 milligram per litre and was gradually increased up to 1.4 milligrams per litre as the site operator became more confident. Cost savings for this site were calculated at £20,000 per annum at the time, and it gave a return on investment of 14 months for the complete installation. This second site is a plant from Germany, and it's of a similar size to the previous example. Here the driver is compliance, as the site had an industrial input from a juice manufacturing factory. The graph here shows how the PRTC responded to different conditions. The blue line is inlet flow, and the red line the dose of ferric chloride. The green is the phosphorus concentration in the outlet. The left-hand side of the graph shows a large storm event where the flow is preceded by an increase in phosphorus, as we've seen earlier. After the initial flush of the system, the flow remains high for some days, but the phosphorus concentration has reduced. When the load is low, the PRTC will apply an agreed minimum ferric dose, probably in this case to aid settlement in the primary tanks. When the phosphorus load returns to normal, the PRTC is able to adjust the ferric dose to achieve the target 2 mg per litre phosphorus in the outlet of the works. The load peak entering the works, presumably from the juice factory, is responded to by the PRTC algorithm, and the dose is increased to counter this effect. And that's seen at the peak marked event. The installation of the PRTC at this site reduced the ferric dose by 60% and guaranteed compliance. The next section is a discussion on the ability to reach low phosphorus consents and the methodologies required. Trials are underway in England and Wales to attempt to achieve sub 0.1 milligram per litre total phosphorus in municipal wastewater discharges. Hach equipment is involved in some of these trials, but it is not our place to comment on the current status of these trials. However, one thing that should be considered is that no salt is totally insoluble in water, and all metal salts dissolve in water to some degree. In the case of ferric phosphate, within the temperature range of pHs found in a wastewater treatment plant, assuming all of the orthophosphate has reacted with the ferric salt, the minimum concentration of phosphate in the water is around 0.1 milligrams per litre at a pH of around 7.5. Should the pH reduce to 7, then the dissociation equilibrium shifts and more phosphate becomes redissolved, giving a value of around 0.2. Figures for aluminium are slightly different, within the minimum solubility occurring at a pH of 6.6, giving rise to values less than 0.05 milligrams per litre. It's my opinion that chemical treatment alone will not achieve the sub 0.1 milligram per litre total phosphorus target requested by the Environment Agency. And in that respect, I'd like to share with you some information that was gained during a visit recently to the Netherlands, where a similar trials took place within 2006 and 2008. During this period, a number of trials were set up in the Netherlands to investigate if the proposed maximum permissible risk values of less than 2.2 milligram per litre of total nitrogen and less than 0.15 milligram per litre for total phosphorus could be achieved. One such trial took place at Leiden Zuidwest wastewater treatment plant. The outlet of the plant was divided between two test streams. Each stream used a moving bed sand filter and involved dosing precipitant and methanol as a carbon source. Stream A had a carbon source and coagulant based on the final effluent prior to the mixed with the final effluent prior to the contact tanks, which then fed a moving bed sand filter, the outlet of which was monitored for total phosphorus, orthophosphorus, and nitrate and nitrite. The second stream had final effluent and carbon source dosed to the moving bed sand filter. Coagulant was added to the filtered water leaving the moving bed filter prior to it entering contact tanks. The clarified water exiting the contact tanks was then passed through a mixed media static sand filter, the same four parameters being monitored at the outlet of the filter as on stream A. Both moving bed sand filters were designed to operate as denitrifying filters, and the dual media filter in stream B contained a top layer of anthracite and a bottom layer being quartz sand. This was backwashed when required. Both streams were able to meet the required target for denitrification and phosphate, but to achieve the phosphate target in stream B, ferric chloride had to be replaced by polyaluminium chloride. However, in the end, it was considered to be too expensive to install this equipment on all sites, and a less stringent target of 0.5 milligrams per litre total phosphorus has now been set across the Netherlands. Only time will tell if this same outcome happens here. More information is available on the low P trials in the Netherlands, and that's available at the Europa EU website at the link shown at the bottom of this slide. That concludes my presentations.
Thanks very much, Martin. Very informative. Hopefully, I think everyone will agree. We've already got a few questions coming through, which is great to see. Just for those who may have joined a little bit late and missed my introduction, just to remind you that the way to submit any questions that you may have is to type them into the bottom left panel on your screen and press submit, and then they should pop up our end and we'll be able to answer them live. If not, we'll take them offline later. So we've got a few questions already, Martin, as I said. First one here, there's a couple of questions from the same person. For what plant sizes is RTC recommended? I dare say they're talking about PRTC.
Yes, yeah. That really depends on if there are issues with the plant. The cost of the system is not insignificant, but with the ever-increasing risks of fines, and those fines aren't going down in value, I would say that if there is a compliance risk, then it could be down to very low PEs of 5,000, something like that, provided we can get a sample. And that's as with all instrumentation, as long as there is enough water there to get a sample, then it could be economic. Okay. And if the network is not combined, that is to say that there's no stormwater arriving to the treatment works, is it still worth installing RTC? Oh yes, yeah. The variations in the phosphorus load throughout the day would still give you savings in phosphorus loads.
Okay. On to another question we've got here. So, is the online monitor only measuring the soluble P, whereas the P consent is on total P? How can this be dealt with?
Yeah, when we are measuring in the feed forward on the inlet, then we are measuring orthophosphorus, and as we mentioned in at the start, a lot of the load is in the orthophosphorus state. But again, you would be looking at the dose taking out the solids as well. So we would be monitoring the outlet when we originally install the PRTC to ensure that we do meet that compliance. So we would be taking out total P as well with the flock that forms up primarily in the primary settling tanks. So it's also possible, although to use a total P analyzer, but we would only put that in the outlet of the works to operate on a feedback system.
Okay, thanks. Next question was, how low can the Ortho P monitor measure to?
The Phosphax SC has a minimum detection value on scale of 0.05 milligrams per litre, so 50 parts per billion. Now, it will actually read below that, give you values below that, but the accuracy then is we're operating outside the measuring range. We have considered this, and if the low P values threatened are actually applied to wastewater treatment plants, then we do have another analyzer which can go lower, but that's designed mainly for industrial applications and doesn't have quite the same enclosure, but it would be possible to go lower with a different analyzer. But currently, for the levels we're seeing at inlets and normal values at outlets, then the standard Phosphax SC is okay.
Okay, great, Martin. Another question here. Is the molar ratio of metal ions to phosphorus, is that relationship linear?
No, it's not actually. It actually increases the lower the phosphorus concentration goes. I sort of relate that to having to chase the ions around to catch them, really. As the phosphorus is getting lower, then it's actually really to do with the energies required to do this and mixing, etc. But yeah, it is not a linear relationship. The lower you go, the more you have to. We found in trials and sort of jar tests, not only from Netherlands also, but you're somewhere between, if to get to the really low values, you're going to have to dose it sometimes around the 15 times the molar ratio, the molarity of precipitant to phosphorus. But at normal levels, you'll probably be around the 3 to 5 times.
Okay. And the next one here is, does the control system take into account biological P removal?
Yes, it does. When we again in feed forward control, we take some measurements of phosphorus take up across the ASP plant, and that is programmed into the RTC system, so that what we don't want to do is starve the biology in an activated sludge plant of phosphorus, which is nutrient, and so you'd stop it growing. So that's what you must not do, otherwise you'll just wreck the plant, basically. So you must keep that, ensure that there's sufficient for the biology to carry out its work as well.
Okay. Another question here. Can the PRTC be applied to 2 dosing points? I think that means 2 points where there's dosing of ferric or aluminium.
Yeah, each dosing point would be well, depending on the layout of the plant, each dosing point may require its own RTC system. I don't know if the person that's asking this question is considering an inlet and outlet of a works. You couldn't, they would have to be totally separate. So you'd have feed forward on the inlet, feed back on the outlet.
Okay. What is the analysing time for a single analysis in your analyzer? And what is the frequency of the sample being tested on crude sewage?
Again, you can adjust that in the analyzer. We would recommend for best response that the analyzer is set for its minimum minimum time period, and that's one result every 5 minutes, but that can be increased if you so wish. Now, if you're interested in measuring total phosphorus on the outlet of the works, that's because of the digestion step, that's a bit longer, and it's around about the 6.5 minutes of cycle time on that one.
Okay. And does that change with crude sewage?
No.
To be
No. It's
no? Okay.
the analyzer time is exactly the same for both.
It doesn't matter where you're analysing in the plant.
No.
Okay. Another one here. Right. Okay. Do you see a significant difference in molar ratios required between ferric chloride, ferric or ferrous sulfate, and PAC or PACl? I think it's aluminium chloride. Isn't it?
Polyaluminum chloride.
Yeah.
Yes, those ratios are different, and they would be. It seems from our experience that aluminium, although it's hardly ever used in the UK, aluminium is more aggressive at taking out phosphorus. But we have to consider as well that the Environment Agency tend not to like aluminium, so the metal consent applied to the site would be lower than if iron was used.
Okay. Another question here. What are the normal ratios between ortho P and total P in crude influent, effluent, PFT removed sludge considered by the Hach system?
Oh, crumbs. To be honest, I don't have those off the top of my head. I'd have to come back to you on that one.
I would say it's to do with it depends how much solids we're talking about,
yeah.
Especially on the effluent side.
Yeah.
So
I think on the effluent side, I believe it's a ratio of around about 3:1, but don't quote me on that one. But they're not stable. That's one thing we have found, that the ortho P and total P ratios in final effluent aren't stable, and that's really relating to solids lost from a filter. So if you're starting to see solids lost, then the total phosphorus concentration will go up in relation to ortho P.
Okay. And the next question is, have we used the PRTC on any filter works or any activated sludge plants?
Activated sludge plants in the UK, yes. I don't know of any on filter works.
I know we've been talking to one of the water companies in the UK about that, but also in conjunction with aluminium.
Yes.
Across tertiary filters. So I think it is possible, but I don't think we've had any experience in the UK of that. We may have in mainland Europe.
Yeah.
Yeah. Okay. Okay. I think that's it. I'll keep an eye on the questions. So if there is any more, then obviously please send them through, and I'll double check that in a while. I'd just like to take this opportunity to thank Martin and thank everyone for all your questions. I think it's been a really great interactive session. Just to answer one of the questions that came through very early on in the presentation about will we be able to get a copy of the presentation. Yes, we'll have a PDF copy that we'll be able to send out to people if you request that. But we're also recording this webinar, and that will be uploaded onto our Hach YouTube channel. So you'll be able to watch that, and the link on that will be sent out as well. Just like to remind everybody that the next webinar in our series, entitled Sludge Thickening Optimization, that's to be held now on Tuesday, September the 20th. So we have a bit of a break now for the holidays. That'll be at 10 o'clock on that Tuesday. Very much like you to join that one as well. It's great to see the amount of people that have joined this morning. Hopefully we keep that up and we keep passing on the knowledge from our side. So we'd like you to join us, but also ask you to forward your invitation to any other colleagues that maybe you may think should have an interest or a benefit from attending as well. Don't think there are any more questions, so that brings us to the end of the webinar. Again, thank you all for attending, and we look forward to speaking to you all again very soon. Thanks very much.